Today I'll present to you a workshop in reinforcement learning. So what will we do today is I'll present some concepts to you guys, then we'll have some time for you to ask questions, and then I'll present some code that you can play with after this session and walk through it and make sure that if you do decide to use it and have fun with it, then how to run it and stuff. So, before jumping into the theory of it, I am curious if you have any favorite games that you like playing, and you can write them in the chat. It can be Minecraft. It can be anything. It doesn't have to be, okay, Fortnite, Roblox. Nice. And have you ever heard of bots that play these games? Solitaire. Yeah, now I'm thinking that you probably met many bots or artificial engines that try to play these games, and I was wondering if you met them before or if it's easy for you to beat them or not. People still writing games. Okay, and would you say these games are strategic or not strategic? Or I don't know if you play them, how can you be strategic or not? Or what does it mean to be strategic in the game? Or short sentence, I think, would suffice. Okay, some of them can be quite strategic, improves problem solving, nice. But I mean, it's not super clear if you were to build AI engine, how you'd make it obey this strategy, no? Okay, I can see that a lot of you speak about like smartness and intelligence, but what does it really mean to build intelligent systems, right? Because, for example, I can build an algorithm that can do quite well. Is that thing smart, or is it intelligent, or is it just an algorithm that solves a problem? Okay, so you're saying that an intelligent system is able to calculate moves ahead and find the optimal. What happens for games like chess where you cannot see all the moves ahead and then there is no optimal, right? Okay, I guess this is like the question of this session. So now I'll go forward and present to you how I view artificial intelligence and machine learning in general. So yeah, let's start. So I'm sure that most of you heard about, AI and data science and so on. And I just want to give you an idea of how I think about it. For example, artificial intelligence started quite a while back, and it started with under fields such as symbolic reasoning or knowledge modeling. So symbolic reasoning was very schematic way of making choices. Um, for example, you have a little robot and you say, okay, if you see something in front of you, you move to the right and then you go ahead. If you don't just go ahead. So this is like a symbolic way to reason, right? But then we have all this world around us and all this knowledge that we'd like to model somehow, because with computer science, you cannot just put images into somewhere, right? You have to find a way to encode them and to write them as something. Then with data science, like under fields of it are like, for example, statistics, where you have a question about the general population and you want to find the answer, but because you cannot ask everybody in your target population the same question, what you do is you take a sample, and then based on that sample, you can find out a truth about your big population. For example, how many people on Earth like chess or Minecraft? You cannot ask everybody, so you just have to ask 100 people what they like. But then it depends what 100 people you like, right? Because what 100 people you ask. Because if you ask young people, you might say, oh, 80% of the population likes Minecraft. But then if you ask old people, they might say, like only 10% likes to play Minecraft. So with statistics, you always have to be very careful with these biases that come around questions, right? And then data science also has like linear regression, so finding out a general truth based on what you know, kind of. In the middle of these two fields, you have machine learning, and then in the kind of under machine learning, you have neural networks that, I think most of you have heard by now. It's a word that has been thrown around a lot. And then you have reinforcement learning, which is what got me into research in machine learning, actually, because it's super fun. Have any of you heard of reinforcement learning before? Okay, so quite a lot not. So for me, reinforcement learning is super fun because it's with robots some of the times. But if you heard of reinforcement learning before, so the thing that is in the red 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 circle. I mean, you don't always have to punish the AI. You can reward as well. Nobody's punishing AI, but okay. I'll show you some examples and like how it all started. So in 1948, it all started with Gray Walter, right? And Gray Walter made two small robots made out of extra war mechanism, and he programmed them to think, to be intelligent. But basically, the program was something like, oh, if your light sensors see light, then you move or something, so it wasn't really intelligent. Or they programmed them in another experiment to see like obstacles that were in front of them, and they wanted to see how well they were avoiding them. But also like this way of uh, acting with the environment was coded into them, right? It was like a logical schema. But while they were doing these experiments with these little cute two robots, they placed a mirror in front of Elmer once, and Elmer started to get super excited, like started to move hectically from left to right, because he noticed that the light in he had a light in front of him that was moving at the same speed as he was doing. So he was like, oh, I exist. And then and then the scientists were very happy to see that a robot realize of its own existence. I'm very happy that did you know Dream of Californication song? Perhaps you can share it with your friends, and maybe not in this session, but these robots eventually evolve into something that we kind of know about now, and it's about this like Hoover robot, which I mean I don't have a Hoover robot, but I mean I like Red Hot Chili Peppers. Okay, it's nice, but yeah, I don't know. I like jazz more too. So yeah, I mean, Hoover robot wasn't able to move as fast as your dog, I guess. But what they're really good at is like at mapping, the room around them, and also avoiding obstacles that don't move with a high speed as your dog does. And yeah, they're like an older version of Elmer that is actually usable and can do something in day-to-day life. Um, yeah, and after that we get to more serious robots. For example, Deep Blue and Kasparov example. So Deep Blue was a supercomputer built by IBM to play chess, and he played with the world chess champion Garry Kasparov in 96 and then in 97. And in 96, everything was okay. Garry Kasparov knew that a computer cannot play chess as a human does, right? And he had a very clear plan of how to beat a computer. But in 97, something changed. And, as we can see here, he lost both in the second and in the sixth game. And these were very tragic losses because the champion kind of got out from his, I don't know, board chess table and left annoyed. And the reason that he left annoyed was that he was arguing that he actually didn't battle a computer, because at one of the moves the computer made um, seemed very human to him. And what does this mean in this concept, in this context? So computers in general, as some of you have said before, are able to see 30 moves ahead, maybe at max. I would say not even 30, because the number of possible positions grow exponentially and there is no computer that can retain so many positions. So let's say 20 positions ahead, and that's the best they can do, like with some heuristics or some smart logic around, they cannot see over 20. But humans have this capacity of seeing beyond 20 moves, because they kind of make strategic decisions that would impact the game much later on. And this comes from playing thousands and thousands of game and kind of training our brain to see so far. We don't actually have to simulate the whole game to see 40 moves ahead, because you kind of get into that mindset of, okay, the position might look that way. So yeah, he made a huge scandal, and because Deep Blue didn't want it to prove that the move was made by a computer, they actually had to burn it. So yeah. To a more happy example of reinforcement learning, we have the Boston Dynamic robots that kind of started between 92 and 2024. They kind of look like this. They have different shapes, and they are forced to go through different challenges and, to open doors and climb stairs and all of that. And obviously, this is not very simple to code, right? Because at the end of the day, you have an object that has multiple joints to control. This object has like sensors that see image, so they need to process at time image and also move accordingly. the whole time, and also compute this whole information that they get. So I have a question for you now. Um, Obviously, these robots have a lot of joints that need to kind of move accordingly at all times, and you need to train them to do so. But do you think they train them in real world or in virtual environments, or how do you think these robots are trained to walk? Okay, and how are they trained in virtual environments? But how do you find um, how do you find this ideal moving of the joints? Is it just trial and error? Okay, trial and error. But okay, let's think it from like a different perspective, right? Let's say that a robot has 30 joints, and these 30 joints can pick between 10 values. How big is the search space? It's quite big, no? 300, I would say maybe it's bigger. Okay, we're getting there. Yeah, with the zeros. There are super many zeros. People got the idea. Okay, and is it, is like trial and error a good way to do it if you have such a huge space just for 1 second of movement? Okay, somebody gave good answer. Nice. Okay, reward and punishment works better. So you have to simulate somehow this kind of the way that they walk, and if they fall, that means that at some point they did something wrong, right? I will ask again because I think maybe I confused you a bit. So we want to simulate the walking of a robot many times, right? Everybody agrees with this? Zero. That's nice. But it's just a sensor, like it just tells you if it's on the floor or not. What I'm talking now is how to make sure that it learns how to move its joints so that it actually stands up. Okay, so make them learn from a mistake is like a one trial, right? How many trials do you think that a robot like this needs to have to learn how to walk? More than 5 trials. Okay, lots. How many? Okay, we're getting there, like again with the zeros. And again, you need a super big computer. So actually, you can do it on your own computer, and you can, train such a robot how to walk on your own computer. You don't need some hyper big computer, and you can use Mujoko DeepMind, which was created in, 2012 to do so. And it is trained with, reinforcement learning and stuff. And I mean, it starts quite rough because our little dude is, falling continuously and having a hard time. But after many trial and errors and, like rewarding good joint movements and punishing bad joint movements, our little robot will be able to walk in a way that is able to maintain a good balance. So yeah, and you know, when you go to uni and stuff, you'll actually work with platforms like this, and it's super fine. I believe you simulate. So this platform, Mujuko, already simulates gravity for you. So the way that it works is that it gives you the robot, it gives you like the environment that has the right level of gravity, and what it gets from you, like the computer scientist, is the joints values at different times, and given that is able to simulate your robot moving and standing up or falling. Okay, so you know, what did we observe in all these examples? So we noticed that we kind of deal with agents, which are these beings, virtual beings, I don't know how to call them, that interact, right? And they interact with an environment, and there is like this continuous interaction between them. The agent makes a decision, and then the medium change, and then based on that, he can make next time better decisions. Or if you deal with chess, you know, like there is no reinforcement in that, but it's more like okay, my opponent made a move and now I'll make mine, and I see again 20 moves ahead and stuff. And all these agents have like a decision-taking mechanism, right? That via this interaction with the medium, they decide whether to move a joint at some position or with some velocity, or they decide that a move is the best, or, you know, for our little Elmer, they decide to activate some engine and just go forward. And, you know, as I said before, it's like what's very important in this kind of interaction is that the medium always feeds back to the agent saying, okay, your agent hit the ground, he fell off. So now you need to train your decision-taking mechanism, you know, you're not performing good enough. So, you know, just to make sure, we have an agent, and this agent has some decision-taking mechanism. The decision-taking mechanism does an action. The action affects the environment changes, and then this goes back to the agent. The environment also can reward or punish, and then the learning algorithm that kind of feeds the decisions that our agent might want to take will change, will tune to take better decisions. Which examples that we covered are agents? I would say all of them are agents. You know, whether you have a body, so this is called like embodied AI. Embodied AI, for example, can be a self-driving car because it has a body that moves through our space. This is an example of an agent, or a chess engine is also an agent, right? Punishments, I mean, reward and punishment are kind of the same, right? I think it depends on your problem a lot. So if you want to make an agent that always performs well, probably you will be very encouraged to reward him. And if you want him to never do any mistakes, you'll probably go more on the punishment type of mentality. Okay, and you know, how do we build like these intelligent systems is the question. Yeah, it's a constant loop of feedback. That's how it kind of works in general. But now, you know, because yeah, so punishments usually count as like a negative number score. and reward is more positive. So for example, if I have, this agent and he's falling, I want to give him a score because that's what machines are able to understand. They understand numbers. So if he falls, I say minus 100. If he falls, let's say in the first second, I give him minus 1000. If he falls in the first 10 seconds, then I would be like, okay, minus 10, because he still was able to walk for like 10 seconds, right? Yeah. So Um, so somebody is asking if you have to tell the agent that -1 is bad for thinking, and for the agent, like how does the agent know that a negative value is bad and he should change his behavior? So usually how agents train is that they try to optimize over a function, which means they try to maximize like a score. So them trying to maximize the score kind of inherently tells them that a small value is bad. Yeah, it's because somebody else asked, how does it know it's a punishment? Again, it's these agents have inherently built in them to maximize a score, and if the value is small, then they know that they haven't performed so well. Okay. I guess many of you know the end of X and 0 on a 3x3 board. Like, if you are the first player, what is the best outcome you can get? Somebody is saying win. What is the best outcome you can get if your player is very good? Or okay, so a draw. But no, it's actually a draw. Yeah, and the best outcome the second player can get is draw. So it's a very depressing game at the end of the day. But how do we know this? And how, for example, we know that if our opponents make this type of mistake. So let's say I start with X in the middle of the board, and then my opponent puts his 0 here. I know I will win. How do I know that's a win? Experience. Analytical skill, yeah, sure. No, it's not analytical game. You just build this huge game tree, and then you do something which we'll learn later how it's called. So like, I mean, if your opponent is very good, for sure he won't want to choose like this type of scenarios that lead to a win, and he will want to minimize your chances to lose. So let's simulate a game with AI, and it's an AI that sees all the possible outcomes. So let's say that I start with an X here, and then my opponent makes the best move possible and puts a 0 in the middle of the table. And then I continue with an X here. And, I'm just, I mean, I know that if my opponent will move this, I have a win for sure. So, of course, my opponent will choose the branch that can lead to a draw. And this way of thinking is almost like I'm always trying to minimize what my opponent can get and always trying to maximize what I can get, right? And because we see until the end of the game, this is very easy to do. But you know, some observations like what happens if we can see until the end of the game? Like, let's say I am on a 6x6 tic-tac board, and I want to make a map of all possible positions. Do any of you can approximate how many positions would that be? I think it's more than 36. I mean, 36 is only at first move. Okay, some people say 36 factorial. How many zeros 36 factorial has? Approximately. I mean, you don't have to be right because I don't know either, so it's okay. Loads. Nice. A factorial is when, so for example, 5 factorial is 5 times 4 times 3 times 2 times 1. 36 factorial is like 36 times 35 times 34 times blah, 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 blah times 1. And this happens because at first move, you have 36 possibilities where you can place your symbol, and then at the next move your opponent has 35 possibilities where he can put your symbol. So this is why you get this growth, because each time at the next move you have a space less where to put your symbol because your opponent already placed it somewhere. And yeah, you know, like it's super many positions, and this is kind of what I wanted to show here, because as position 0 nothing is there, but after one move I can put it in 36 places, and then at the next move opponent can put at 36 times 35, and you know, it's a lot. So this is problematic for computers because obviously computers don't have infinite memory or infinite processing power, right? Like when you deal with so many zeros that you say lots, it's probably not good for your computer. So you need a way to tell your AI that a position that is a middle position, so neither a win or a lose, is kind of good or kind of bad. So, and this is what I mean by scoring earlier on. So this is very similar to how our little robots kind of learn how to walk, right? And just out of curiosity, so if this is like the first position and this is the second one and this is the third one, if you were to offer scores from 0 to 100, 0 means very bad position and 100 means very good, and for X, what numbers would you offer? Use a quantum computer, maybe in 30 years. Yeah, so 1 means very bad for X and 100 means very good for X. And you have to give 3 numbers because there are 3. Yes, so X has the next move. Okay, so I see that some people like the first position more. I see some that like it less. And you know, when you see this for the first time, what I'm thinking is, I don't like this position for X because X is not that central, and also now there is a 0 very close to it, so I don't have many possibilities on how to win. But in the second one, if the game is to have like 5 consecutive X's in a row, this is actually a winning position because I can just place an X here, and then you know, whether zero place it's zero here or in there, I'm still going to win the game. So actually, yeah, Andrew, for example, said that the middle one is 100 because it is a winning position. So we can, you know, tell the computer, even though we are not at the end of the game, if you have 3 X's in a row and no space at either ends, then you're probably going to win. And this way of thinking is called a heuristic, and it's very, very used in reinforcement learning. On the other hand, so now we have a way of scoring positions that are not ending positions, right? So let's just say that we play like this game of X and zeros on a very big board, and these are the scores that we get at some position that is ours. So we want to maximize. And let's say, you know, that our player also sees these scores. So our opponent is able to see kind of how the board will look, you know, in I think this is like 4 moves. So when our opponent sees these scores, of course he wants to minimize our performance, right? So the way he'll think about it is, so if the game evolves in this way, and my opponent can make a move that is a 5 or can make a move that is a 6, I will, of course, he will, of course, pick the move that is a 5 and not a 6. And, you know, like in this case, if my opponent can make a move that is a 8, 9, or 10, of course, you'll pick the 8 and so on. So I can assume that, you know, my opponent will always make the moves that minimize the score of the position. So, you know, as we can see again, for example, our opponent had to choose between a board that was valued as a 100 and one that was valued as 200, and he picked the 100 board scoring thing. And then, you know, when it's our turn and we want to maximize the score, for example, you know, of course, if we are in this scenario, we want to pick the board position that brings the most score to us, so we'll pick the 100. And because I want to make sure that people are listening, I'm curious, in this minimizing node, what do you think the next value will be? Okay, 5. Nice. 23. Why? Is that your lucky number? Okay, so, you know, it is indeed 5. And then, of course, you know, when it's our move and we want to maximize, of course, we will pick the scenario that wants to maximize our, I don't know, advantage. And this algorithm is really demonic in terms of, you know, if I show it like this, most of you might look at it and be very scared. What's happening here? But it's very similar with what I have been speaking about, you know. So, for example, if the depth of our kind of way at looking at a game is bigger than 3, then we return this heuristic value of a node. So this, you know, like intermediate function that doesn't really know if it's the end game or not, but yeah, just says something about the position itself. Then if it's the maximizing player, so if it's me that plays, then, you know, I want to pick the best value that I can for the next possible positions. And yeah, I mean, more with this algorithm I can't explain now because you're not really familiar with recurrent algorithms, but try to kind of get the intuition for it, because I mean, if you are interested in computer science, you'll learn about it at uni anyways. So what did we learn today? We have these agents, right, that continuously interact with an environment via action. The environment changes, and then the agent kind of notice this change. And also the environment rewards or punishes the agent, and by reward, its learning algorithm gets tuned to maybe take better decision next time, and then, you know, so on. And now I want to show you some code that you can have fun with. So I guess for later. So I guess if you can write this down somewhere. And while you do that, if you have questions about this presentation, also feel free to write them. So with the heuristic. So the heuristic is just a function that tells you a score for a position that is not terminal, and it's you can also take a picture of the link, because it's like a really nice code base you can enjoy if you are interested into this kind of stuff. I can also send the link in the chat. Ah, nice, thank you. Yeah, I mean, yeah, heuristic sounds weird. First time when I heard it, I was very confused as well. I didn't know what to make of it, but yeah, it's basically just a scoring function that tells you how well you're doing without knowing if you won or not yet. And a heuristic is what tells you these values in a middle game. So if you play chess, for example, you see 5 moves ahead in, you know, all possible possibilities, and 5 moves ahead, you have some ideas of how the board might look like. And if you win a horse, then that's good for you. So you have a heuristic, right? For example, for chess, there is like this heuristic that tells you that if you have a horse, you have 3 more points, or a queen is like, I don't know, if you have more pieces, this can be a heuristic as well. And it's just a way to score a middle game position that neither has ended or started. Any other questions? So now I'll kind of show you how to play around with the code. So, and if you have questions, I can answer while I show you as well. So if if you play on this, like if you press on this like Colab link, it will lead you to a Colab notebook. And these notebooks are quite nice because, I mean, if you first make a copy, you can you can run some code and then play X and 0 with the AI. In order to kind of run this type of stuff, you have to press on this running bubbles each time. And I already did that. And now I'm going to try to play a game. So does anybody have any proposals for possible first moves in this game? Top left, okay. Top left is 0-0, I think. Okay, our opponent played it in the middle. Now? Bottom right. Okay, that's 2-2. Yeah, middle bottom is quite sad now. It's already a draw. And yeah, top corner is like 0-2. And unfortunately, it's a draw because, you know, he sees all the, yeah, it's, I know you wanted bottom middle. You would have resulted the same because the AI engine sees the end of the game. But I mean, you can have fun with this thing because the further work for this notebook is that you can implement your own 6x6 board tic-tac-toe. And as we know, you know, computers cannot really simulate the end of this game. So you can build your AI engine and then beat it. And then build a smarter AI engine and beat that too, you know. So I'll just show you around. So this code, you know, usually, I mean, this is quite demonic and I don't expect any of you to understand what's happening here. This is the print board function that prints a board and realizes this beautiful user interface thing. And also we need a function that checks wins and stuff. So, you know, in our case, the win condition is like 4 symbols in a row, column, or diagonal. And then we arrive to problem 1. So, you know, problem 1 is like, yeah, fix this min-max function. So if you open up this bubble, you'll see a min-max function for a 6x6 board. And because I know it's quite nerve-wracking to look at something like this, I also put like messages to not change anything in this section because you might break. So yeah, you have to fix errors in this section in order to make it work. And I don't know, do any of you see maybe any mistakes on these lines? So no. Yeah, I feel like this is the type of thing you want to. Okay, you see a error where? So to make it easier for you, you actually have the code implemented for a 3x3 board. And you know, on your free time, like after this session, you can look over this, and this is complete. Is correctly implemented. I see that some people are upset about the minus float infinity thing. That's not an error, unfortunately. I'm really sorry. It just means like minus infinity, because when you're maximizing, you want to the scores that you will compare against later on to be bigger than something. So of course you have to start like from minus infinity to compare, you know. Yeah, and I mean, some obvious errors that, for example, I see in here is that the rows and columns are in range 8, but our board is like in 6x6, you know, so I'll just correct that very quickly. And for example, I'm looking at this line and this one, and there is a col -1 that looks a bit weird. So I'll look again in the already implemented min-max and see. It's just a row call. and delete that. And, you know, maybe the code will run now. And it didn't have errors, and now I want to simulate it. But because the game is very big yet and we don't have a heuristic, you know, like this code will never end up running, basically. Or I don't know, you can wait a lifetime to see. Oh, nice, somebody saw the range error. Good, nice, well done. So, you know, after this, the second problem is to implement your own heuristic function. And this can be done very easily with ChatGPT and other language models, which I really encourage you using if you're new to coding. They're very good at implementing very easy functions in general. And I mean, yeah, you can just put this in ChatGPT and see what it does. And then the last part of your homework, if you want to explore more into this, is like code a proposed idea and play with your own intelligent AI XN0 on a 6x6 board. And I think this is pretty much everything from me.